In this video, we'll see how to work out linear combinations with different vectors. For example, suppose that we want to find out if the vector w shown over here is a linear combination of the vectors u and v. So visually, what we can do is the following thing. We know that multiplying a vector by a number changes its size. So in this case, let's look at what happens with u times a scalar. Here, I'm defining that scalar to be a. And notice how whenever I change the value of a, the magnitude of that vector changes. That means the size of the vector changes. If I multiply by something bigger than 1, the vector becomes bigger. Whenever I multiply the vector by something smaller than 1, that becomes smaller. And if I multiply by something negative, changes direction. Same thing happens with the vector v. Whenever I multiply the vector v, I can enlarge it, shrink it, or change its direction. Whenever we do this, we're basically changing the size of this vector. And we have two new vectors, the blue and the red vector. With these two new vectors, what we can do is we can add them together. So if I call w prime that addition, we have that addition changes whenever we change those parameters. Now, in order to visually see a little bit better what's going on, what we can do is we can visualize the sum by the parallelogram visualization. In this case, that means that we can translate this u prime into the tip of the vector v prime, and then this will form a parallelogram with the vectors that we're adding. Notice how the vector u double prime is just a copy of the vector u prime. The only difference is where it starts. The vector u prime starts at the origin, and the vector u double prime starts at the tip of the blue vector. So this makes it easier to find out what is the addition of these two vectors. We just have to put the tip of one to the tail of the other one, and then the resultant is going to be the sum of these. So my original question was to find if there was a linear combination that will give me w, which means that I would like to see if I can adjust these knobs so then I can make coincide the green vector with the black vector. So it seems that if I just put this close enough, that would be a good approximation. It seems that the actual values will be 1 and 3. But visually, finding these parameters could be not enough, could not necessarily help me with the actual values. So it is much better if we try to do this in a more systematic and algebraic way. So let's see if we are not just lucky and if these numbers actually give me the values. In order to do that, what I'm going to do is I'm going to work out the vector system of equations. So I have the vectors over here. Vector u is the vector 1, 1. The vector v was the vector negative 1, 2. And the vector w is the 2, 5. So we want to solve for this vector equation. We want to find values of scalar ab such that au plus bv equals w. Which means if I put it in vector form, that a times 1, 1 plus b times negative 1, 2 equals positive 2, 5. Which means that I have an equivalent system of equations. I could also write down this as a system of equations. This will become a plus negative b 2b equals 2, 5. And then if I put these together, that will give me a minus b. A plus 2b equals 2, 5, which gives me the system of equations a minus b equals 2 and a plus 2b equals 5. So either this representation or this representation basically are telling me the same thing. So what I'm going to do is I'm actually going to use the third type of representation for this system, which is the matrix form or the matrix representation. And for this, what we're going to do is we're going to look at the augmented matrix for this system, which could be thought as the coefficients of the system of equations, or just joining the vectors that I have in my vector equation. Either way, we will get 1, 1, negative 1, 2, augmented by 2, 5. So all these three different representations actually represent the same system and the same problem that was to find the actual values for this scalars A and B. So what I can do is I can use the reduced echelon form in order to find the A and B. So if you remember, the whole point of the reduced echelon form is to get rid of this number, which is not going to be a pivot, and eventually we're going to get rid of this number because that will be on top of a pivot. The resulting form will give me the solution for my matrix. So I can do, what I can do is, first of all, I can replace the second row by, say, the second row minus the first row. And that will give me 1, negative 1, 2. And then I will subtract these two things. That will give me 0. 2 minus negative 1, that will give me 3. And 5 minus 2, that will give me 3. This is very convenient. Now I can replace the second row by a third of the second row. And then this will give me 1, negative 1, 2. 0, 1, 1. And then finally, I can get rid of this top negative 1 just by adding the first row and the second row together. So we can replace the first row by row 1 plus row 2. And this will give me 1, 0, 3, 0, 1, 1. And this means that A equals 3 and B equals 1. And that's exactly the same values that we found visually in my previous animation. So that means that actually, yes, we could trust that animation over there with the exact values. And it's no surprise that I will get the actual numbers over here. So we have three different ways of representing the same problem. We have the vector way, we have the system of equations way, and we have the matrix representation. Now, the advantage of using the last one is that we have a very systematic way in which we can find a solution. Namely, we just find the reduced echelon form, and that will give me the answer.